Good day to you. Today let us see how to protect IGBT. I don't think this is being taught in colleges or universities. Many may not be knowing these basic concepts. But once a circuit has been properly designed, one can protect IGBT without any failures while they are working in the field. But if it is not properly designed, then there is likely to have many failures while it is working in the field. Conventional method of protection. This is only for the interest of history or something like that. Copper wire is being used as a fuses. Even now, people are using copper wires for fuse. In India, Tamil Nadu, maybe in everywhere, copper wire is being used at HT fuses in main transformers, distribution transformer in the HT side and LT side also they use copper fuses, copper wires as fuses. Every copper wire of some size has a limiting current. Beyond that, it cannot handle. What will happen if the overcurrent flows? The copper will heat up and it will melt. So then and then it will break the circuitry. So this is how copper wire fuses are working. And then what came is a HRC fuses. HRC fuses are used in industries to protect the current given to various loads, but here this is not being used for protecting any IGBT or MOSFET because IGBT or MOSFET are much more faster devices than HRC fuses. So these HRC fuses are useless in protecting IGBTs or MOSFET. Even the glass fuse also cannot protect IGBT or MOSFETs. But people have designed some special purpose fuses to protect thyristors. Long ago, I was using such fuses. So, thyristor will have a rating of I square T. How much current it can handle in a particular time. That is called I square T. So, fuses also will have the same type of rating. The fuses will have its maximum current, rupturing current mentioned in I square T format. So, I square T of fuse shall be less than the I square T of thyristor. Then, whenever there is a heavy current, fuses will open first and protecting the thyristor. But nowadays, I don't think anybody are using thyristors in the power conversion equipments. Maybe very low people who are following the old technology may be using it, but others don't use it because circuits using MOSFETs, IGBTs are much cheaper and then easier to design and fabricate and then install at the site. As I told you, to protect MOSFET and IGBT, fuses are useless since they are very slow to act. So we have to find some circuitry to protect them. We will see one by one in the coming slides. There is something called safe operating area for MOSFET and IGBT. Let us look at this graph. What is below the graph is a safe operating area. What is above the graph, non-safe operating area. There is a line starting just above the 10 and goes upwards and travels in a horizontal line and sharply comes down at 100. So what is below this line is safe operating area. What is away from the line is unsafe operating area. So what we can infer from graph is when the voltage is beyond 100 for this device, the device will fail. So this is very clear that there is a maximum VCEO for IGBT or VDS all for MOSFET. This the device cannot work beyond the designated voltage, drain source voltage. Similarly, any current beyond 400 ampere for this device, the device will fail. But within the limit, say assume okay, the device you can pass 400 ampere for 10 microseconds. The device can handle 400 ampere for 10 microseconds. So this is a safe operating area. If you allow 400 ampere for 20 microseconds, it may fail. Look at the graph of 10 millisecond. It can allow 1 ampere at 100 volt. Look at the graph of 1 millisecond. It can allow nearly 4 to 5 amperes at 100 volts. So whenever your voltage and current are well within this safe operating area, the device will not fail. If you exceed it, the device will fail. But this graph is fully dependent on temperature of the junction. If the junction temperature increases, that current rating comes down naturally. So the designer has to keep the current and voltages of a device within this limit so that this will not fail. There are two methods of protection for MOSFET or IGBT. One is current sensing, another is VCE SAT sensing. SAT stands for saturation. VCE saturation voltage. Let us see first what is current sensing. So in this circuit you can see a resistor or shunt. Generally it will be in milliohms range. So whenever current flows through resistance, there will be a voltage drop. The voltage drop can be measured and then corrective action can be taken. So this is called current sensing. There are some IGBT gate drivers available based on the circuitry also. This is VE SAT sensing. This is we sense the voltage drop between drain and source or collector and emitter while the device is on. When the device is off, full bus voltage will be available across this point, but when the device is on, the voltage between drain and source or collector emitter will be very low. This voltage will increase when the current through the device increases. This increase in voltage is detected to device protection. The voltage drop between drain and source or collector and emitter are sensed and then corrective action will be taken so that MOSFET or IGBT does not fail. Kindly look at the circuit. This is the practical circuit designed by me. You can see two diode D6, D7 connected to the drain. So when the MOSFET is off, it will see the total bus voltage. So but no voltage will be passed on to the pin DSAT. DSAT will not see any voltage. Maybe some leakage, could be some spurious voltage, but when the MOSFET switch is on, the voltage measured or voltage sensed DSAT pin is VCE SAT, the saturation voltage across the drain source or collector emitter plus the diode drop. So when the current increases, the voltage across the diode, the voltage across MOSFET or IGBT will increase, and the increased voltage DSAT sensed and the pulse to the IGBT or MOSFET are removed. This protection is without any external control from microcontrollers. So without any intelligence, the MOSFET driver itself gives the required protection, overcurrent protection for the MOSFET or IGBT. Seen so far how to protect the device from overcurrent. Now we have to see that the device doesn't see over voltage. See, every device MOSFET or IGBT will have a maximum limiting voltage. We should see that the limiting voltage is not exceeded. We have to connect one TVS diode across the MOSFET or IGBT. D9 is the device to protect the MOSFET or IGBT from over voltage. The D9 has to be carefully selected. The working voltage shall be higher than the bus voltage. At the same time, the clamping voltage shall be lesser than the drain to source voltage or collector emitter voltage of the device. If this is not properly selected, then D9 may not fully protect the IGBT or MOSFET. R2 and C9 as rubber circuit, they are introduced to reduce the voltage spike across S and D. So we have seen so far how to protect the MOSFET and IGBT. Thank you for watching.